Sound check. Sound check. Sound check. Sound check. Sound check. Okay, guys. Hey, I think we're just about ready to go now. So let me just load up the right page. I want to start with complex numbers and then we'll go to the other two. Okay. All right. So let's just pop that over there. Okay, complex numbers question. Let's just sort this out. Yeah. Okay, so we've got this complex numbers. So I'm just checking that we've got everything. I think it sounds coming through okay. Just give me a shout on the chat if anything's not quite working right. All right, so we've got this equation z cubed is equal to this complex number here. We're told k is real and positive. And we want to write our solutions in polar form in terms of k. Now that actually is giving us a clue as to how to approach this. That is first to turn it into polar form, and then we will use de Moivre's theorem to be able to find the roots. Okay, so if we think about this in polar form, we've got it over here in the positive quadrant for both x and y. In the x direction, we've come across by k, and in the y direction, just there, hang on, let me just draw that properly. We have, it's gone up by root 3k. So this just here is root 3k in the I direction. Okay, so now we can use that to do some Pythagoras and trigonometry and work out the hypotenuse. So first of all, the hypotenuse here is going to be k squared plus root 3k squared. So root 3k all squared. So that will give us a 3k squared. So we've got 3k squared plus k squared. And that is equal to 4k and 4k squared. And if we square root that, we will get the hypotenuse is 2k. Now you might also recognize that this is actually a similar triangle to the special triangle that you have on your formula sheet that looks like this. It's just all of the sides have been multiplied by k, which means that the angle we have here is the same as the angle that is there. That one's on your special triangles, and it's listed as pi by 3. Now, if you're not sure about that, you can just use trig to work it out, but it's helpful to be able to pick up those quick things of knowing and recognizing that that's a special identity triangle first. Okay, now why does that help us? Now we can write z cubed in polar form, where the modulus is 2k and the argument is pi by 3, like this. Now that's helpful because we can now use de Moivre's theorem. So our first solution to this will be to do the cubed root of everything. So when we're cube rooting complex numbers that are in polar form, we cube root the modulus and we divide the argument. So the argument now will be pi by 3 divided by 3, which is going to be pi by 9. Now that gives us our first solution. So if we were to plot that, it would be somewhere here, where we've got that angle of pi by 9 and the modulus is root 3, cubed root of 2k. Now, roots of equations that are like this, if it's written as z to the power of something equals, then those roots will be symmetrical around the origin with however many we have. Now we know we have 3 roots, so the other 2 roots will be at an equal distance around that circle compared to where this one is. So our full circle is 2 pi by 3, and we need to divide it by 3 so that we know the gap between each of our roots. So it's full circle divided by 3, that's going to give us the gap from our first root to the next root. So now our next root will be to do cubed root of 2k, because the distance away from the origin hasn't changed, but we will take our argument and add on 2 pi by 3. So I'm just going to go over here to check my fraction adding is okay. So 1/9 plus 2/3 is equal to 7/9. So it's going to be the cubed root of 2k cis 7 pi by 9. So that one ends up being on our diagram sort of about here. There's our second solution. Now I know that my next solution, if I was to add another 2 pi by 3, I'm going to tip over that pi line into the next quadrant over, and when that happens we know we actually go back around the other way. We come under our graph and turn it into a negative instead. So I'm going to go straight to doing that. So our third solution will be to take, let me see if I can just clear that off a little bit. Take the one that we have at this time, come back around this way. So we're going underneath, we're going to subtract 2 pi by 3 off of the original one that we had, being the pi by 9. So that's going to be cubed root of 2k cis of pi by 9 take off 2 pi by 3. So that's cubed root of 2k, and then we've got 1/9 minus 2/3 is equal to negative 5 pi by 9. Now the alternative way of working these ones out is that you add 2 pi to the original amount, so this pi by 3 in the cubed thing, you can add the 2 pi there and then do the whole thing divided by 3. Does the same exact outcome for those. Okay, for this one I am expecting the achieved is sitting at finding the first solution. I'll just go check that for you. If I can bring that up on my other screen, just a moment. Where are we? Okay, one of those solutions correct would get you the achieved, so it's going to be where this first one is. So getting as far as figuring out that much, that's your achieved point within this question. Okay, now on to differentiation. We've got a curve is defined parametrically by these two equations. Find the gradient of the normal to the curve at that point, at the point where t is pi by 4. So we need to differentiate each one. We've got dx by dt. So if we differentiate that, well, the 3 doesn't change anything, it's just a multiple on the outside. Cos differentiates to minus sine, so this will be minus 3 sine t. Similarly with dy by dt, then sine differentiates to positive cos. This time we have a 3t inside, so we need to multiply by the 3 because it's chain rule. Let me just make that a bit clearer. There we go. So dy by dx is equal to 3 cos of 3t over minus 3 sine of t, because we do, oh wait, sorry, I've skipped a step and hold on, give me 1 minute. We'll do dy by dt times dt by dx, so you can see what I'm doing. Okay, so we've got 3 cos 3t, and dt by dx is, I've just lost my mouse, there we go, is the flip of dx by dt, so we turn that over and put it on the bottom of the fraction here. Okay, the 3's obviously cancel, so we're just left with this. Now when t is equal to pi by 4, then we can pop that in. We'll do cos of 3 pi by 4 divided by, it'll be negative sine of pi by 4. And that is 1, which almost feels too good to be true. It's come out so nicely. So the gradient of the normal is the negative reciprocal of that, so that'll be minus 1. Okay, I'll go have a look at where the achieved point was given there. Oh, I've lost it. Hang on. Going to have to go to... Oh, I'm pretty sure it would be at this point just here is where you're going to get your achieved. It might even be for getting both of those two correct, but just to be sure, I think it would actually be putting it together here. Sorry, I lost the mark scheme just then. Not sure where it's gone. Don't want to waste too much time looking that up. Okay, but it's fairly straightforward to take that all the way through to merit. Okay, finally we have integration. We've got these two areas. We have the curve of minus x squared, so that'll be this one, minus x squared plus 2, and the cubic x cubed minus x squared minus kx plus 2. And we want to show that those two areas are the same. So we need the intersection points first. We'll do that with x cubed minus x squared minus kx plus 2 is going to be equal to minus x squared plus 2. Okay, so those two cancel with those. We've got x cubed minus kx equals 0. So take out a factor of x and we've got x squared minus k is 0. So x equals 0, which we can see is this intersection point there, or x squared equals k, so x is plus or minus root k. So we have a root here, an intersection point at root k, and we have an intersection point at minus root k. All right, now area A, we will get that by integrating between minus root k and 0, and we're going to do the cubic minus the quadratic, because the cubic is on top. So this will be x cubed minus x squared minus kx plus 2. Take away the quadratic. Okay, now that minus of the bracket, if we multiply that out, that becomes a plus, and that becomes a minus. So those two cancel. And if we integrate x cubed, we get x to the 4 over 4. If we integrate minus kx, we get minus kx squared over 2. And we're subbing in the values of minus root k and 0. Okay, so substituting those in, we will have 0 when we put the 0 in. Take away. Okay, negative root k, if we do that to the power of 4, root k times root k is going to be just k, and the negatives cancel out. So then we've got root k times root k times root k times root k, so we've got k squared over 4. Now, if we put it into the squared, minus root k times root k is k, and then we've got another k to times it by, so that's k squared over 2. So we have a quarter minus a half. That's going to be a negative quarter, and then times it by the negative makes it a positive quarter times by the k squared. So this will be a quarter k squared, or k squared over 4. Similarly for b, but we're going between 0 and root k, the positive one. And this time we have the quadratic function minus the cubic one. So what we had in this, the first line for a, just here, we're just going to reverse that. So this time we will end up with it being kx minus x cubed, because everything would just, the subtraction would have been done in reverse. So you could write it out again, but it's going to come out to that. So we have very similar, but with opposite terms, like this. Oops, let me just tidy that up. 0 to root k. So then, going through the same process we just did a minute ago, but in this one, if we put root k in for x squared, we will get k, then it gets times by k. So we've got k squared over 2 minus root k to the power of 4, that gives us k squared over 4 for the first one, subbing in root k. And then if we sub in 0, we just get 0. Okay, so this a half minus a quarter is a quarter. So we have k squared over 4, and you can now see that those two are equal. So therefore, area A equals area B, because they're both equal to k squared over 4. Okay, let's see if I've got the mark scheme for this one open still, and we'll see where the achieved point was at. Okay, so getting the integral right for either of those, so that is this point just here, or this one just here. One of them would have been worth your achieved. So achieved here, or achieved there. Okay. And that takes us through your 3 merit questions for today. Done pretty quickly again. So then let's see what questions we've got. Okay, could you please run through it quickly? I just want to double check I know what I'm doing. Malika, what is it particularly that you want to check? Was it complex numbers, integration, or differentiation? I'll just give it a second. I know there's a bit of a delay between asking questions and it popping up on here and then you hearing it back from me. If it was just the integration one, then the basic premise of what we were doing here is that, let me just get that so we can see as much as we can on one screen. Actually, what I might do is pull some of it over to the side. Oh, actually, that's going to just make it worse. Okay, so we've got the 2 curves. We want the integration to find the area between them. And okay, so just the last question. I'll just take you through the steps again. We needed the intersection points first. So we set the 2 curves equal to each other and use that to work out where those intersection points are. So now we know we're integrating for part A, we're integrating between the first intersection point and the middle one. We do a subtraction between the curves so that we can find the area that's between them. So that's this one minus the other curve, and the minus I took the bracket out and turned that into just reversing the signs there. A lot of those terms cancelled, so that was helpful. So we were just left with x cubed minus kx. Integrate both parts there. Let me just tidy that up so it's not in the way of what I'm talking about here. So integrating the x cubed got us x to the 4 over 4. Integrating the minus kx gave us minus kx squared over 2. And then we substituted in the 0 and the negative root k. And that gave us the k squared by 4. Then you do the exact same thing for b, except this time we're going between 0 and root k as our points of intersection. And because it's the quadratic that's sitting on the top, we do that one minus the cubic. And if you do that, it simplifies to this. And then it comes out to the same answer. So you know you've got the area of A is equal to the area of B. Okay, hopefully that was useful. If there's any other questions, I'll stick around just for a little bit. Feel free to drop them into the chat there. Okay, glad that's helped you, Malika. And good luck with the rest of your revision for the exams.